This talk now is about the BSides Entertainment System, wearable gaming for your princess is in another castle, and it's given by Peter. So let's thank Peter for this presentation.
Thank you, Kylie and Silvio. Very much appreciate the talk, and I appreciate all the effort in organising this conference that you guys have put in. So my name is Peter, and when I grew up, I played so much Nintendo with my brothers. It is insane. And my parents just waited forever for us to get sick of it. And I loved Game Boys when I was growing up. And then when I went to uni, I learnt about programming and software development. And I hope one of the things I convey with my talk here today is when you want to find something to work on, what you want to do is you want to take something that you're really passionate about. For me, it's Game Boys and Nintendo, and your skills, which for me is software, and then you can make your own awesome projects. And if my talk inspires you to go off and break something, then that's awesome. Anyway, we'll get started. Okay, so again, my name is Peter. I'm currently employed at Pen 10. Again, grew up with Game Boys. If you looked at my Steam account at the moment, I haven't bought many games, but I have a whole bunch of Nintendo emulators on there. So I'm a bit crazy. And this is my phone that I've attached Switch controllers to. Did anyone notice the animation? No? Oh, okay. Just a couple of disclaimers before I get started. I did not write the emulator that I used in my talk. I ported it to the BSides badge, and I'll give credit to the guy who did. I will not do anything illegal before, after, or during this talk. I have no connection with Nintendo, and I am not representing them in any way. And if you choose to do some of the stuff that I've done to my badge, and I'll point out the dangerous parts, I'm not responsible if it stops working, because I've almost had that happen a few times. Okay, so we'll start with a quick letter from the princess. So I'll go through the 2016 badge. I'll talk about how I selected the emulator to use. A bit about the device, so it's comparing the badge to the original NES system. Refactoring, which was basically about getting the code to compile in the first place. Hacking to actually make it function. All the bugs that I found along the way and had to resolve. Optimizations to make it run faster, and it's still not quite there yet. And then how I had to reiterate again when the new 2017 badge came out. Oh, and I got the 2018 one to work as well. Oh, thank you. Okay, so the 2016 badge. All right, so you can read up the specs online, but it's a pretty powerful little badge. In fact, when I saw the specs, I had a dream for a long time that I wanted to build my own Game Boy, and this badge looked like it was the perfect opportunity to do it. It had buttons, it had a screen, why not? The Nintendo Entertainment System, my first console when I was growing up. It's an 8-bit system. It's got a 16-bit address space, which the cartridges add to the address space. About 2 kilobytes of RAM, which is about over 1 million times less than your laptops. And most importantly, it was one of the first systems to have a custom picture processing unit. And this made it easier for game developers to write code because it handled things like characters on the screen and scrolling the screen across. And so it's pretty cool, like some of the features it had in it for its time. Again, why do this? Well, I've kind of said Game Boys. And also the NES Classic is like still $300 on eBay. Like it's actually gone up in price. All right, so I want to put a Nintendo on it, got to find an emulator. So I love C++, and I know it's going to make a whole bunch of Erlang and C developers cringe in the audience. Sorry. But so my language and the compiler Arduino look like they're all good. I want to be able to see Mario, so I want a screen that works. I want to step on the bad guys along the way, so I want some kind of input, which I never got working, sorry. And here their screens. Sound was a complication that I just didn't want to have in this project, so I kind of put sound outside of the scope of this project. So when you start looking for an open source library online, have an idea about what you want. For me, I wanted the emulator core, the thing that emulates the system, physically separated from the software that presents it. And that way I can swap the view to actually be the screen on the BSides badge. And the controller is the thing that kind of joins those two together. So it tells the emulator about the screen, and it tells the screen about the emulator. And if you look at source files, you can actually kind of get an idea about how well something's been structured. So the emulator I chose looks pretty good on the surface. I need to be able to compile it. And if it takes me too long to figure out how to compile it, I'm just going to move on to the next one. Like, I don't really want to spend my time figuring out how to compile stuff. And I can't believe it. Someone wrote unit tests for an emulator. Like, that is so awesome. And when you see unit tests, it gives you an idea about the quality of the product that you're actually getting as well. And so this guy, Daryl Yu, it was his emulator that I ported. There's a GitHub link address there. So if you're in the audience, thank you very much. Happy to talk to you afterwards. All right, so let's do a bit of a comparison. The original NES ran at about 2 megahertz. It's about, and then the badge itself is at 80, so 40 times faster, and I still can't quite get it playable. But when I was looking at it, 40 times faster, that's a pretty good ratio to do an emulator. Color screen, looks great, no worries, that should be easy to do. Memory, it's got about 90 kilobytes of memory on the badge, and I probably only need about 32 to actually make it work, so I've got enough memory. Storage, it's got 1 megabyte of flash on the badge. Put it in perspective, a 3.5 floppy disk had 1.4 megabytes, so it's a less, but we should be able to fit it all on there. Now, I looked into being able to load games from the SD card, but given the way the badge is designed, I would have to share the bus to the SD card with the screen, which would slow down the graphics. So I thought rather than doing that and risking slowing down the device any further, I would just burn the ROMs into the program and then flash the whole thing onto the badge. So it only runs a game at a time. And when I say slow, I mean like the Star Wars opening credits scrolling slow. So I never got a controller to work. I just didn't really have time at the time when I was doing it. This is a schematic for the original NES controllers and how they work. If you're curious, look it up online. It's pretty simple the way that it does a latching system. Anyway, if you're a nerd like me, maybe worth a read. So now we have an emulator and we have a device and we need it to compile. We need the code to be compatible to be flashed onto the device. So this is what I thought I got. This is what I was hoping for. This is what actually ended up happening under the hood, where the emulator, the graphics, it all knew about each other. So the first part of refactoring was actually just separating out the code. So the emulator had no knowledge of what the graphics system was. And when I say graphics system, I mean the Windows graphics system or the Arduino TFT library. And this is what I ended up refactoring it to. So I had my main program, the emulator, and some DirectX graphics stuff, which is great because I can keep the same emulator and swap it to Arduino and use the screen. So I can actually test my code on a Windows PC, which is far faster than flashing every time I want to try something. And then when it's good to go, I just hit recompile for Arduino, and we're good to go. So storage-wise, I'm only using about 62% of the 1 megabyte on the device, so storage, I got plenty. But RAM was a different issue. So my laptop has like 8 gigabytes of RAM, which is like millions times more than what's on this device. And I got out of memory warnings when I was compiling it. So what I did is I moved all the memory allocations in the emulator right up to the top of the program and then handed it in. And that allowed me to measure how much memory was being used by each component. And on my first cut, I needed about 400 kilobytes of RAM on a 90 kilobyte system. So it was a bit depressing at this point because it looks like it's not going to work. So what do? We start hacking, because that's what we're all here to do, right? We're going to fine-tune it until the square peg fits in the round hole. So the biggest culprit is the screen. You've got 256 by 240 by 4 bytes per pixel, so that's already about 250 kilobytes of memory that we need to basically shrink down. So the first thing to know is that the emulator was using 32-bit color, but most of your phones and screens only use 16. It's an 8-bit system. Nobody's going to know the difference. So we'll just halve the amount of bytes needed per pixel, and we can halve the storage. Done. So then I found out that the actual LCD screen has about a quarter of the pixels of the original NES. How did you do it, Silvio? How did you pick a screen that has lower resolution than the original Nintendo Entertainment System? But turns out you can use this to your advantage, because if you only have a quarter of the pixels, you only need a quarter of the storage. So it was like a bonus in the end. So all I did was every time I had a screen, I added up 4 pixels, took the average, and said that's the color. And then it's like, well, why are they still doing a whole picture of rendering at a time? The original NES worked by drawing a line on your old CRT at a time. So looking a bit deeper in the emulator, I found the piece of code where it was basically accumulating lines, storing in a picture and then handing it back. And I hooked it earlier, so now I only need 1 row of pixels at a time. And now we've gone from 250 kilobytes of storage, of RAM, sorry, to 1 kilobyte, which is pretty good, I thought. And then we had RAM. So the actual RAM is like a pre-allocated buffer for the NES, and all the games get loaded into it. There's no way that I can sacrifice 65 kilobytes of storage. So I ended up reading the game as it would in the actual system directly off the flash rather than loading into memory. But I'll get a bit more into that later on. So I finally got it down to about 87% of memory usage. And at this point, you start getting warned by the compiler saying, hey, look, if you want to flash this on your device, you go right ahead, but I think there could be problems. And then, obviously, things don't necessarily work straight away when you try and recompile it. So it's a constant cycle of compiling, fixing compiler bugs, going back, compiling again over and over and over again. And then you get to the fun part where it finally flashed onto the device and it doesn't work. And you get the blank screen of death. So I don't know much about the internals of the emulator, so where do you start? There's this idea in programming of Indianness. And if you want to think of it, when you go to the shops and you buy a slab of beer and you put it next to your fridge at home and you're taking beer cans out of the box and putting in your fridge, Little Indian is about whether you stack the shelves in the fridge from left to right or right to left. And so given that my Windows machine stacked it left to right and my badge stacks it right to left, I just looked through the code for all places where it was doing this behavior and added some extra code checks. So then it actually started running and I got a stack trace, and Arduino didn't really have a debugger that I could configure at the time. So I basically added a whole bunch of print statements to the code until I found out the exact line. Turns out with Arduino there's a different memory copy function called memory copy P, and that's what you use to basically take from flash and put it into memory. And then I got my first opening screen. I'm like, yes, it's working, but it's blue. And I had gone through all these little Indian cases. But it turns out that because I knew it was the color, all it was is that, think about it being red the other way around, the blue pixels being red is red and vice versa. So look through the code for all the pixel handling, found the spot, and it still crashed. So what I was doing is I had the emulator running inside one loop of the device. And there's this concept with embedded devices of a watchdog timer. And you are responsible for calling the watchdog timer reset, because if it doesn't happen, it will reset the device for you. And that prevents your device basically hurting itself when it gets into a bad state. So every time the emulator rendered a frame, I just called watchdog timer reset, and it was all good. So my dog is getting a walk roughly 30 times a second, so she's pretty happy. Oh, and that's my dog Ada. She's pretty cute. And we got it working. Woo. But it was really slow. So now we're going to find all the ways to make it run faster. First easy thing, we're just going to halve the frame rate. Now, I know for gamers in here that are operating at 144 hertz, 30 frames per second is probably going to hurt your head, but you've got to do what you've got to do. But it's not as bad as trying to do interlacing, where basically on odd and even frames, you decide to render odd and even lines, and it looks terrible. In fact, if you try and back up a DVD, some of them are actually interlaced, and you get the same kind of effect when you play back the backups. So the other thing is that the screen doesn't change too much on the old systems. So you can actually add up all the pixels in a line and create what's called a checksum, and then only choose to draw a line when the checksum changes. So this added a fair bit more speed, although it adds speed depending on what's happening on the screen, so it has side effects as well. And then you can actually, rather than sending it a pixel at a time, if you know that you're going to have to render 5 red, 3 blue, 1 red, a couple of green, you can actually tell the LCD that. You can say, I want 5 red, instead of saying, I want a red, 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 red. And so that actually makes it run a bit faster. You can also overclock it. So on your badges, you can actually call this function and make it run at 160 megahertz, which again, I don't know how long my badges are going to last being overclocked. And then you can actually overclock the SPI bus as it goes to the screen. Now, I don't know whether you can see it. When I put it up to 40 megahertz, what happened was that the data was being sent to the screen so fast, it couldn't actually catch all the pixels. And so you start to see little imperfections on the screen because it's being sent too quickly. So I took it down to about 25. And then I thought, well, what if instead of reading from the flash every time the game wants to do something, I actually implement a paging system? And I never quite got it working. It crashed a lot, but the few times it actually did run through, it was like playable kind of fast. So a little bit more to work here, and I think it would be like almost usable. So still a work in progress. And then came the 2017 badge. But lucky for me, Silvio tweeted his workshop. And I don't know whether you guys can see on this picture, but the actual badges were on it too. And you could actually see the pinouts, which basically indicated to me that he was going to use the exact same microcontroller. And also there's a row of pins on the top, which suggests he's going to use the same screen. So when I got my badge, I thought, no worries, I'll just flash it. And it didn't work. So I was like, okay, well, I fixed a whole bunch of problems. It's got to be something to do with the wiring. Now, normally if you're doing PCB work, you have a schematic to work from. I didn't have that. If you actually do things the right way, you can use a multimeter to actually see where things are connected. I didn't think to do that. I trace the circuits on the PCB one by one and figured out by reverse engineering the wiring for the LCD, for which 2 wires were around the wrong way. I highly recommend the multimeter approach. It would be far quicker and frustrating than what I did. And then it kind of worked, but the color's wrong and it's around the wrong way. And I looked at forum after forum online, trying to find someone, trying different things. And I think that's a big important thing. When you're doing your own project, you're going to be prepared to try a whole bunch of stuff that might break what you're working on. But then, got up and running again. So that was pretty good. I was pretty happy. That's about it. Any questions? Oh, hang on. COV's coming up.
Over here.
How hard was it to get the 2018 badge going?
Sorry, could you repeat the question? Sorry.
How hard was it to get the 2018 badge working?
The question was, how hard was it to get the 2018 badge working? Besides me trying to wire it up and sort of see how it worked, it wasn't too bad. I think my soldering and my shaky hands was the biggest barrier to what I was doing. But essentially, what I ended up doing was wiring the screen from the 2017 badge to exactly the same pins on the micro, so the code just worked. So I took the easy way in that respect.
Are there any more questions? One over here.
Did you consider any other hardware modifications to make changes to the software easier, like adding more RAM or something?
Okay, the question was, did I try any hardware modifications to make it run faster or make it easier? It was actually suggested to me later last year, and I didn't actually get around to it, but absolutely adding some more some more RAM to the side of it would have made some huge improvements. I did just get working before I came here, a Wii Classic controller working. You can get little PCBs that click on the bottom of it. I don't actually have one here, unfortunately. I was in a bit of a rush this morning. But yeah, you can actually get NES Classic controllers to work with the badge. It's basically just an I2C bus. So, but that was really the only other hardware modification I tried.
Any more? Let's thank Pete.
Thank you very much.